Hello everyone! This video is about non-deterministic Turing machines and why they have the same computational power as deterministic ones. This means deterministic Turing machines, or DTMs as I will be calling them, can recognize and or decide the same languages as NTMs. This works because you can simulate any NTM using a DTM, and that is exactly what we're going to talk about. Here's our example language L. The NTM that will accept L we will call N, and this will be our example non-deterministic Turing machine. L will consist of any string of A's of length 1 or of an even length. So examples will include 6 A's, 1 A, or an empty string because 0 is an even number. Here's the state diagram representing N. This is based on N's transition function. The arrows represent transitions that are possible based on specific configurations. The left character on the arrow is the current tape contents, and the right character is the direction that the head will move in that transition. Other state diagrams you may have seen include something for the head to write down as it moves, but in N we're going to be simply reading the tape. We're not going to change it at all. In determinism, a given configuration, which is the current state, the tape contents, and also the location of the head, which we will show in a second in an illustration. So any given configuration yields one and only one other configuration. So in this example, if you're in state Q1 and you read a blank symbol, you go to state Q reject. That's the only thing that's possible given that configuration. Non-determinism is when a given configuration can yield more than one. And we have an example here where N reads an A in state Q0. It can either move to state Q1 or Q3. So if it's in this configuration, in state Q0, the tape contents is A, and the head is in the first position, it can either move to this configuration, Q1, or this configuration, Q3. Now let's look at two computation trees. These trees are models of the transitions or computations N will make given a specific input. So this is the computation tree for the input of an empty string. We start at Q0 because that's the starting state. N reads a blank symbol and then it moves to Q accept. That's the only transition that it makes. This is the tree for the input of a single A. We start at state Q0 and then the non-determinism takes over. It can either move to Q1 or Q3. Those are the two possible transitions or computations. If it transitions to Q1, then it'll go to Q reject after reading a blank. If it transitions to Q3, it'll go to Q accept, also after reading a blank. Regardless of how many branches reject, if any of them end in an accept state, that means the machine accepts the input. So N will accept input A, as we've talked about. Okay, now let's get into how to simulate a non-deterministic Turing machine with a deterministic Turing machine. Here's our non-deterministic computation tree based on N's transition function and the input of two A's. First, let's kind of understand a model of how our deterministic Turing machine is going to work. Like let's visualize what type of computation it's going to do. So basically our machine is going to search this tree for any accept state. Our instinct might be to search each branch to its end. That would be called a depth first search. The thing is that doesn't work because any one branch might infinitely loop and then our machine will be stuck there. So if this branch infinitely looped, we'd just keep searching down here and we'd never reach this Q accept. Instead, what we should do is a breadth first search. This is where we check each node from left to right and we go down by rows. Our machine will need some way to keep track of its location as it searches the tree. So imagine each node is assigned a numerical label. The leftmost node is 1 because we took the first branch, and then this would be 2. We add digits based on which numbered decision we took to get to each node. So this node, we make decision 2 and then decision 1. It doesn't matter if there's only one decision, we still count it as 1. So then this node's location is 2, 1. We understand the number of locations. We understand that our machine is going to search through these nodes in a breadth first search order, but how is it going to know which nodes to visit in which order? For this, we're going to create an algorithm. Now, to understand this algorithm, we're going to start with B, which is the maximum number of non-deterministic choices any node in the computation tree can make. In our example, B equals 2. I'll scroll back to show you. Node Q0 can make 2 choices, and that is the most number of choices that any of the nodes in the tree can make. So B is 2. Then imagine a set of strings containing all the whole numbers from 1 to B. So if B is 5, this would contain the strings 1, 2, 3, 4, 5. In this case it's 2, so our sigma simply contains string 1 and string 2. So what the algorithm is going to do is iterate through the set sigma plus. Now to understand this, sigma plus is very similar to sigma star, which you might be more familiar with, but it doesn't include the empty string. So the plus operator, when applied to sigma, is going to attach any number of strings in sigma together to get a new string in all of the different possible combinations. So it's going to take string 1 and string 2 and basically put them together in every possible order. Now our algorithm is going to run through the members of sigma plus in order of the number of digits and numerically. So it's going to go through the members with 1 digit and then the members with 2 digits, and within those groups, depending on digits, it's going to run through them numerically. So it's going to run through them in the order shown on screen. Now that we understand the algorithm, we would construct a Turing machine that implements it. It would take B as its input and it would write each successive member of sigma plus onto its tape. So this is what its tape would look like. Go through all of the members of sigma plus. If you want further explanation on how to construct this Turing machine, such as an implementation description and the drawing of the state diagram, you can watch the video that I've put in the description. I should put timestamps there, and that will provide a good explanation that is too detailed to go into here. For our purposes, we're going to take this Turing machine and make it part of the larger Turing machine that we're building to deterministically simulate N. So this is a model of the larger DTM that we're building. It's going to have 3 tapes. Multi-tape Turing machines are equivalent in computational power to single-tape ones, but I'm not going to go into the proof of that there. That is another thing that you can look up. Maybe I'll put something in the description. Yeah, I'll put something in the description for that. So first we're going to go through all of these tapes, but first let's wrap up our understanding of the third tape. So the third tape of our M is going to be the tape of the Turing machine that we talked about 2 slides ago. The idea is that M has to take N's transition function and go through it in a deterministic way, and tape 3 serves as the extra input to take these non-deterministic choices and make them deterministic. When M consults N's transition function and is confronted with multiple options, it's going to look at tape 3 to see which choice to make. And the algorithm behind tape 3 will make sure that these choices are in the order of a breadth first search of N's computation tree. So it'll tell it to make the first choice, and then the second choice, we go left to right down this tree. This is why I'll be referring to the contents of tape 3 as a path. You can imagine it as a list of directions for M to take when confronted with N's non-deterministic transition function. Now let's talk about the other 2 tapes. The first tape is where the input goes, and that's not going to change as M goes through its computation. The second tape is the simulation tape. This is where all the computation is really going to happen. If this was an NTM, this would be the only tape that we would need. Now that we understand the purpose of the 3 tapes, let's talk about how the machine runs as a whole. Basically, it continually cycles through a loop. This loop starts by copying the contents of tape 1 onto tape 2, and then having tape 3's algorithm generate its first path. There are 3 conditions under which the loop resets. Tape 3 runs out of numbers, tape 3 gives an invalid path, which is when tape 3 tells M to make a decision that just isn't a possibility, and we'll look at examples of that, or M reaches a reject state. Resetting consists of clearing tapes 2 and 3, and you repeat this loop until each branch has been explored, each branch of n's computation tree. Once each branch has been explored, if you only encounter reject states, reject the input. If you ever encounter an accept state, accept the input. If every branch of every tree ends in a halting configuration, your machine decides the language. If it ever loops, then it's a recognizer. Now that we understand a high-level description of this machine, let's get into an example. First, the input, which is 2 A's, goes onto the first tape. Second, we copy the input onto the second tape. Third, our third tape algorithm generates its first number, or its first path. Here's a better view of our tape 2 in its starting position. M sees this configuration, and according to n's transition function, it has 2 choices to make. So it consults tape 3, sees a 1, and makes the first choice, moving on to this configuration. There are no more symbols on tape 3, so we reset the loop. The loop starts again by copying the input back onto tape 2, and you might have noticed that we've cleared tape 2 only to replace it with the same thing. This reset is included in the loop in case we're simulating a NTM that alters its tape, maybe by writing something. We're using a read-only example, so the reset doesn't appear to do anything, but it is a crucial part of the general function of how to simulate NTMs. Then our third tape will generate its new path, a 2. We make the second choice of n's non-deterministic transition function, and we go to Q1. Again, we run out of symbols on tape 3, and the loop resets. The loop starts again by copying tape 1 onto tape 2, and the next path is generated, 1, 1. From here, we take the first choice to state Q3, and now our configuration looks like this. And then the head on tape 2 is reading an A, and according to our transition function, there isn't any additional configuration to yield. If you're in state Q3 and you read an A, there's nowhere to go from there. This means there's no first choice to make, so it's an invalid path. And we reset the loop. So tape 3's next path is 1, 2, which again is invalid. Another way that you can visualize the invalidity of a path is by noting that there isn't a corresponding location on the computation tree. So there's no location 1, 1, and there's no location 1, 2. I'm not going to show all the details for the path 2, 1 because it runs out of symbols. It's the same thing we ran into with 1 and 2. Then we skip all of these because they are all invalid. As you see, there are no numbered locations. Finally, we get to this iteration of the loop. We copy tape 1 onto tape 2. Tape 3's algorithm generates the path 2, 1, 1. M will move from this configuration. It will take its second non-deterministic choice into this configuration, and then it continues down into this configuration where its head reads a blank and then it accepts. I hope this video was helpful. I hope you're walking away with a better understanding of non-deterministic Turing machines and how to simulate them deterministically. Have a good rest of your day.